Kirtana, you can start now.
Okay, sir. An investment in knowledge pays the best interest. A very good evening to one and all gathered here. I am Kirtana A from the Department of Electronics and Communication, here to volunteer and compare today's webinar on the topic Basics of Antenna Process by Ms. Camila Caroline Rodriguez. Now, I'd like to mention our beloved chairman, Dr. B. Babu Manoharan sir, and our managing director, Mrs. B. Jessipriya ma'am, and our director, Mr. B. Sasishekhar sir, and our principal, Dr. P. Ravichandran sir, for giving this wonderful opportunity to conduct this webinar. And special mention to our department heads, Dr. C. Nyanakausalya ma'am, Professor in Head, Staff and Student Affairs, and Dr. G. Rohini ma'am, Professor in Head, Lab Affairs, for their guidance and constant support. Now, let me take the honor of introducing the speaker of the day. Ms. Camila Caroline Rodriguez is an postgraduate student in electrical engineering in the field of telecommunications and electronics at Federal University of Campina, UFCG, Brazil. Ms. Camila Caroline had completed her bachelor's degree in electrical engineering, telecommunication control and automation, electronics and power system engineering at Federal University of Campina Grande, Brazil. She has also completed electronics, computer science, and network engineering specialist in electronics for embedded systems at Grenoble, France. Ms. Camila Caroline also have a great experience in working as an English teacher in Yazigi Internex Campina Grande and had done internship in conception, design, fabrication, and validation of antennas for sport events at Grenoble, France. She has also worked as a junior engineer in the development of low-cost HF RFID system at Signo, Campina Grande, Brazil. Ms. Camila Caroline has also done many researches and laboratory works. Specifically, she had been a student researcher in development of RFID tags and circularly polarized antennas in radiometry laboratory, Federal University of Campina Grande, Brazil. She has been a chairperson of IEEE UFCG student chapter of Antennas and Propagation Society, and then she became a treasurer of IEEE, and then now presently she is being and chapter activity coordinator of R9 IEEE Antennas and Propagation Society. Before we begin the session, we have instructions to be followed by the participants. Participants, kindly post your queries and doubts in the chat box. We'll be discussing at the end of the session with the speaker. Ma'am, I now invite you to begin the session.
Thank you very much for this kind introduction. As Kitana said, my name is Camila Albuquerque, and I'm currently in my master's degree in the Federal University of Campina Grande here in Brazil. And I am also serving as the Region 9 IEEE Antennas and Propagation Society Chapter Activity Coordinator and Student Design Contest Coordinator worldwide. And I'm also now the Student Chapter Treasurer of our local APS UFCG Student Branch Chapter. So my presentation today is based on my experience working with this area of antennas. Even though I am still on my master's degree, I believe I work with antennas for about 6 years now. And since my beginning in the research field, in research area, I'm working with antennas, tags, RFID, and I believe I have some experience, and I hope to share today with you with the basics antenna design process. We are going to talk about conception, simulations, and the measurements. So I'm going to follow this agenda. First of all, I'm going to talk a little bit about antennas in general. Then we're going to talk about the conception, simulation, and measurement. And then I'm going to draw some conclusions. So first of all, what is an antenna? Why do we need it then? So the antenna is the part of a transmitting or receiving system that is designed to radiate or to receive electromagnetic waves. This is based on the IEEE standards for definition of terms for antennas. So the antenna is the part of the system that send and receive the electromagnetic waves, which is very important, especially nowadays that we want things to be wireless. So to do that, we need antennas. And that's why antennas are a very important part of research that we should develop research projects. And it's been it has been a lot of time that we already are improving the antennas, and we are still improving them. And I believe this is a continuous process that is never gonna end. So we have a lot of kind of antennas. We have the big ones that are used for radio systems, from communication systems, from television systems, and also we have the integrated ones that are used most on printed circuits. And of course, we have this one. There is the 5G antenna, one of them. So we have a lot of models. Antennas can be as big or as little as you need for your project. And it is important to know some of their aspects. So when we are talking about conceiving an antenna, what should I think of? So at least in my experience, the main parameters, of course, that we are gonna to look at is the design. Or so, do I need a big antenna? Do I need a small one? Can it be square? Should it be circle? So I should think about the physical dimensions of my antennas, and also the design is responsible for the other parameters, which are the frequency. So which frequency do I need my antenna to work on, and the bandwidth, in which frequency range I want my antenna to work. It's gonna be a broadband antenna that is gonna work in a very large frequency range, or it should be a very specific frequency range that I need it to work on. And also radiation pattern, which is the spatial distribution of the of an quantity that can characterize the electromagnetic field generated by the antenna, which is usually expressed as a mathematical function or a graphical representation. Then I'm going to show some examples for you. And the quantity that are most often used to characterize the radiation from an antenna are proportional to or equal to power flux density, radiation intensity, directivity, phase polarization, and field strength. So linked to the radiation pattern, we can talk about directivity and gain, which are the ratio of the radiation intensity in a given direction for the antenna to the radiation intensity average over all directions. So do I need my antenna to send its power in all the directions in the same way, or should I need an antenna more focused in one direction especially? And then also we have the polarization, which is a very important parameter that depends on my application. So if I, for example, if I need an antenna to make an RFID system, my tags that my antenna is gonna read, are them linear or circular polarization, circularly? So that should be also a concern when you are developing an antenna project. For example, if we're gonna develop an antenna for an RFID system, in my case, for example, I design an antenna microchip antenna, which had the dimension were not very restrict, but they should fit some mechanical space. So I had the design. And then the frequency, I had to work in the standard RFID frequency, which in Europe is 868 megahertz. And the bandwidth is also standard, so we cannot pass this bandwidth, and we should have it very precisely. Another thing is the radiation pattern. I needed my antenna to be in the directivity and gain. I needed my antenna to have a very large gain, and the radiation pattern should be normal to the antenna plane. And also the polarization. In my case, I needed a circular polarized antenna. So these are for some examples of what you should think when you are developing an antenna. Of course, there are a lot of other parameters that can also be crucial to your project, but that will depend. Based on my experience, that those are the main parameters for me, which I usually look at and design my antenna to fill the requirements. So we talking about simulation. When you think about your antenna, you have to measure it. But if you are gonna think in the antenna design, and then you're gonna use the equations to achieve the antenna design itself. And if you are going to always be manufacturing and then measuring, maybe it's gonna be a very very costly process. So we usually, what we do, we have our design and we simulate it with softwares, with electromagnetic softwares. For example, we have the ANSYS HFSS, which is very widely used. And we have also the console, multiphysics, and the CST. And we also have another ones, but those three are the ones that I have most familiar with, especially the HFS, the ANSYS HFSS, which is the one that I'm gonna focus here. And later I'm gonna show you some quick tutorial about how to use it. So for the ANSYS HFSS, we have a lot of possibilities. I believe I work with ANSYS HFSS for 5-6 years now, and there are still a lot of tools that I don't know how to use it, because it's a very robust system, a very robust software. There is, for example, you can simulate the electromagnetic field in a plane, in a car. If you have a phone, how it's gonna interact with the body. So there's a lot of possibility, and it's a very complete software that you can explore and have and search for what you are needing. For example, here, if you want to design an antenna, you can use the HFSS antenna toolkit, which have a lot of types of antennas that you can choose from. And then you're gonna put your parameters here, and it's gonna synthesize and make the antenna for you. But if you need a very specific antenna design, you can do it from the bottom with the elements, the cube element, the sheets element. So you can design it yourself with your CAD talent. And so this is the first part, which is designing your antenna. After you have your antenna ready to go, you can, here is the menu that you have here in the side of the antenna, where you can have, you have all the information that your design need. For example, the citation, where is the feed is going, in this case here. And then we have the setup, so you can put the frequency you are working with, the sweep, so which frequency range do you need the analysis to be done. And then you have the results, which you can plot a lot of different results. Here we did the S parameter plot, the S11, and gain. Also, we can plot field, and I'm gonna show you a little bit more in the next slides. For example, here we have the gain plot. So when you select, when you have here in the results, you can have a lot of different results here. And in far field report, you can have this gain report. And you can see how your antenna is working, the radiation pattern, of course, in 3D, but you can have also in 2D representation. And you have a lot of other options here that I never used, for example, but I'm still searching and still learning to use this software, even though I have a lot of work done in it. For example, you can, in the ANSYS, you can already plot your FFT of your answer. For example, you have a S11, you can plot the FFT and see how the frequency is, the frequency range is distributed in your design. And we have a lot of options. Here we have the gain. Also, we can put this gain in the antenna design, so we can see graphically how the antenna is propagating its power, its sign, and receiving, of course. So here, for example, is a patch antenna. You have the gain normal 90 degrees from the antenna plane, as expected. And the back lobe here is very small, so it's a good antenna, let us say. And also, for example, here when we talk about when you gonna make a solution data report, we can plot, for example, the S parameters. Since here it was an antenna, I have only the S11, but if I had 2 ports, I could plot the S21 and 3 ports S31 and go and all those options of the port as parameters for boards. We can also plot the impedance parameters and a lot of all those parameters that you can need in your project. So for example, here we have a S11 parameter, and we can make the analysis then. What do we need? What is the resonant frequency? So we have an example of the S11 that we can plot with the HFSS. Another thing that we can do in this software is to plot, for example, here the field of the antenna. So here we can see the electric field, but we can also plot the magnetic field, the current density, the quality factor, and others. So we can see here how the electric field behaves in our antenna, and based on that, we can make adjustments, we can make analysis. So it's a very nice tool also when you are developing your antenna project. So now I believe I'm gonna show you a little tutorial of ANSYS. Let me put here. So here we have the ANSYS software, and we have already an antenna here. I'm gonna show you how to make it. This antenna from the beginning. So you open your HFSS software, and you can have a lot of different circuits design here. But we are going to do a 3D design, electromagnetic design. So we're gonna choose this option here, instead HFSS design. So we have the clean page here with the axis, and we can, for example, begin our project from the bottom. We can use those elements, for example, here a box, a cylinder, a regular polyhedron, and a lot of other tools. So for example, here we have the 2D elements, a rectangle, a circle. And for example, if we need to do a substrate, we can have the box and we just draw here. So it's a CAD work here. So we can do that. And then if you need a copper layer here on the top, you can use the sheet, and then you have to place it here. And to do that, what I learned to be the best is to give variables to all your dimensions. For example, if you have a rectangle here, it's your substrate. So here you have all your elements, and here is the box one, which is your substrate. So you should name it here substrate, so it's easier to you. And then you can choose here the material. And for example, if you're gonna use a FR4, which is the most used in my case, we just put it here. And then here you can make the dimension of X size. We can use a name that substrate X, and then you put the length, for example, 5 millimeters, and it's gonna change your design. So you put the positions and the sizes, and so you can have control of your design. But today, if I'm gonna do this from the bottom with you, maybe I'm gonna take a lot of time. But so we're gonna use a tool, which is we're gonna put here ACT antenna toolkit, which we have here. When we open that, the AST extension, we have the antenna toolkit here. We have other kits, toolkits, but we're gonna use the antenna toolkit as I show in the presentation. And we have here a lot of antenna types if you need one of them. For example, if we're gonna design a patch antenna, we can choose from a lot of kinds of antennas and feed options, fed options. So let us wait. For example, here I'm gonna use a rectangular inset fed antenna, a microchip. So here's the model, and we can use, for example, I need an antenna for example, in my RFID, the RFID standard here in Brazil is 950 megahertz. So it's in gigahertz, sorry. So there you go. And then outer boundary radiation, okay. And then it's gonna, let's choose the material here. I'm gonna do an FR4. And the height of my material, which here it's 1.6, it's millimeters, so it's 1.16. And then I can put here synthesis, and it's gonna calculate all the dimensions for me. And then I click and finish. So it's gonna do its job. As you can see, there is a lot going on. And it's done. So here it is, the antenna that the software did for me, and it doesn't do only the antenna, it does all the setup simulation for me. For example, here, if we can go here in analysis, it did the solution setup and S parameter sweep from 0.45 gigahertz to 1.37 with 100 points. And it also did a sweep here with 3 points to see the antenna gain characteristics, a fast frequency, a fast analysis here. And then we have the results. It's already plotted here, but to see those results, we should simulate it. So let's just put here and analyze. Let's wait. While it's simulating, we can see all the plots it has done. Here is the gain. We're gonna see the gain after it's done the simulating part. And then we're gonna see the gain in different frequencies. And then actually here is the radiation part in 2D. And then here is in the different frequencies. And then we're gonna see the return loss, which is the S11 of the antenna. And then the input impedance with a Smith chart. So it's some options of what the software can do. And another thing that we can notice, I'm gonna wait it until it's done. But if we click here, we can see that all the design is with the dimensions in variables. For example, the patch X dimensions is here. So if you change the value here, it's going to change in your design. After the simulation, we're going to show it. And the patch Y is also here. And then we have the variables divided by categories. And the substrate, the feed dimensions, so we can change it based on our requirements. We can also do an optimization of those variables using this Optmetrics tool, where we can use here optimization, automatic optimization, or we can see all the results from different parametric. For example, patch X, we can put a range here and see the results for each variation. So I believe it's done, the first one. Let's see the gain. Here we have it, the 3D gain. We can also have the 2D in 0 and 90 field is 0 and 90 degree. You can plot whatever angle you need when you click in the design. You can see this. And we can also have here the gain in different frequencies. For example, here in almost 500 megahertz, we have the radiation pattern in 2D. And we can see all the in 0 and 90 degree for 3 frequencies here, but you can also change those parameters in the setup here. And for example, if you want the different degrees, you can select the graphic, and then you can change here, for example, the families and the trace. And so it's there are a lot of possibility. The S11 here, as we can see, is not a very well matched antenna, but we can change it by changing the design, and also the input impedance here in a Smith chart. Here, as I was saying, you can change the design parameters by changing those dimensions. For example, here we have 7.8 patch Y, and if you can choose, for example, for 8.5, it did something here, but maybe it was not noticed. Let us change to 10. So you can see that it make its change here, patch Y, we can, for example, 8. So you can change all the parameters here and then simulate it again and see the results and do your project development. So let me go back to my presentation. So after all this simulation process, you have your antenna ready in simulation part. It's working as it should. You're gonna manufacture it. So at least for me, the most common fabrication process are the automatic PCB manufacturing machines and the etching process, which is, I believe, the one that we use the most. And it's simple to do because anyone can do. You don't need a machine to do it. So, for example, here we have a simple microstrip antenna. Actually, those fabrication process I'm talking about microstrip antennas, because if you're gonna do a bigger one, you will need maybe some another fabrication methods. But for microstrip antenna, we usually use those two. And after you have your antenna manufactured, you're gonna measure it. So here are I'm gonna show you some equipments, the most used equipments to measure the antenna performance. And here we have the VNA, which is the Vector Network Analyzer, which is an instrument that measures the network parameters of electric networks. And they usually measure the S parameters because the reflection, which is the S11, and the transmission, which is the S21, for example, S31, are easy to measure. And but they also measure, depending on your equipment, Y parameters, Z parameters, H parameters, and there are a lot of different different things that these equipments do based on the manufacturer that you buy from. Here, for example, we have two. This one is a bigger one that we usually use in our laboratory, the first one. And the second one is the portable one that we use also. But these are some examples. Also, we have the spectrum analyzer and the RF signal generator, which are usually used combined for measuring antenna parameters. And of course, if you need a very precise antenna measurement, maybe you need an anechoic chamber, which is a room designed to completely absorb reflections of either sound or electromagnetic waves. For example, here we have, I believe, the largest one in the world that can fit easily in a plane and a lot of other things. And here we have a smaller one when you have just an antenna. And we can see those blue elements here are the absorbers. So this antenna, as I said, it absorbs reflection. So you have exactly what the antenna is sending and receiving. You don't have reflection reflection effects on your measurement. And to measure the antenna design and performance, we have usually the parameters that we measure are the S11, the reflection coefficient, and the transmission coefficient, which is the S21, or if you have more than 2 ports, S31, S32, and go and so on. And also the gain, which the gain is usually linked to the S21 if you use the freeze formula. I'm gonna show later. And you take the data in a CSV file or SP1, SP2 file, and then you plot and see the comparison with your simulated and measured results. And also the gain, usually you plot in a polar plot. So the vertical and the horizontal is the co and cross polarization. As I said as I showed in the HFSS, you have the 0 and 90 degree of phi axis. So here we have the method that I usually use to measure the gain of an antenna, where we have 2 antennas. Usually the transmission one is a horn antenna, and we have a polarization positioner, which is gonna turn this antenna in 0 and 90 degrees, and your antenna under test is going to turn in a table, in an azimuth turntable. And so we have the positional controller to turn this antenna in several degrees depending on your necessity to plot your polar plot. And this one, both antennas are connected to a VNA in port 1 and port 2, for example, and I'm going to measure here the S21. With the S21, we can measure the gain of the antenna under test based on this equation, the freeze equation modified. When we have the antenna gain of the gain of the antenna of reference, the one horn antenna, which we usually have the gain values in the manufacturer datasheet, and then we can measure based on the S21, and here we can calculate it with the S11 that we measure easily with for both antennas, also with the VNA. So here's the method that I use to measure, and I believe we have all the steps done. We conceived the antenna, we simulated, we fabricated, and then we measured. And that's it for today, my talk. Thank you very much for the invitation for St. Joseph Institute of Technology. And I hope I could pass a little bit of my experience, what I use, and I hope it can be useful for some of you students or even professionals.
Thank you, ma'am. Thank you for sharing your experience. Now, let's move on to the question and answer session, ma'am.
Yeah.
Yeah. The first question is, what is the frequency range required for 5G technology, and how do you design an antenna for 5G?
Yeah, actually, I believe there is more than one frequency range for the 5G. I'm not very familiar with the antenna development for 5G, but I believe it's more than one frequency range that should be researched. And to develop it, you're gonna see what's the parameters needed to the 5G antenna. For example, the one that I showed is a very large one, which it's not a microstrip antenna. So, but if you need, for example, a 5G antenna for your cell phone, maybe it's gonna be a microstrip one with a flexible material, maybe. So you can adapt your design to the application that you're gonna use it. So the 5G, it's a frequency, and it has a requirement setup. So based on this setup, you can manufacture, you can design your antenna. But I'm not familiar with the exactly frequency range. I should maybe make a research about it.
Okay, ma'am.
Yeah.
The next question is, what are the measurement techniques used to design 5G antenna?
the design techniques.
Yes, ma'am.
As I said, I'm not that familiar with the 5G antennas, but I believe it's the same one from all the applications. You need to see what is needed from your antenna. So you are develop a 5G antenna, so you need to see the frequency it's working on, where you're gonna put this antenna, what is the mechanical physical space that you're gonna put this antenna, what are the effects, the field in the place. For example, if you're gonna put in a cell phone, what the metallic elements of the cell phones gonna, how they gonna affect your antenna. You need to see a lot of those requirements to then develop your antenna, and you can put all those effects, those elements that can affect in your design in the HFSS, for example. As I showed in the airplane, you can put all the airplane there and see how the wave is propagated there. So I believe yeah, you need to be very specific on what are you designing. You can also use, for example, antenna arrays if you need to improve your antenna design. But there's a lot of things that should be researched based on the application, a specific application that you are developing your antenna.
Okay, ma'am. The next question is, which tool will be user-friendly to design an antenna?
Which tool
Will be user-friendly?
to design?
Yes, ma'am.
Actually, I believe that the HFS, for example, is a very friendly user software, because I know that at first you can think it's a very complex one. As I said, there is a lot of tools there that you can use, but after a while, if you practice it, you're gonna see that it's not that hard to use it. For example, as I show, you can have already models of the antennas that you may need, and then you're gonna practice the it's a CAD talent. It's a CAD skill that you have. So if you use it in other softwares, you can also use it in HFSS. I also use the ADS, I believe, from Keysight, and it's also a nice software to use. The CST and the console, the CST I already used, but I thought a little bit harder to work with. The console I never use it, so I can't speak on this matter. But I believe HFSS is a good one to start. It had a lot of tutorials on the internet, so you can start from there.
Okay, ma'am. Thank you. The next question is, what value of gain is said to be good antenna or perfect antenna?
Of what?
Value of gain
From which kind of antenna?
for a perfect antenna or a good antenna.
Perfect antenna. All right. That is not a set answer, because that depends again on the application. For example, in RFID, good antennas with good gains would be around 10 to 11 dB, dBi. dBi. So, for example, there is also antennas with 17 dB of gain. That will depend on the application and the frequency you are working with. And usually higher frequency have a higher gain, but for example, if you need an antenna to read closer, you don't need a very large gain, so you can improve another requirements, because sometimes if you improve the gain, you can lose in other uh, design requirements. For example, usually higher gain antennas have higher dimensions, have larger dimensions. So if you need a small antenna, you probably won't have large gain. So it depends on your application. You have to make a compromise between the parameters that you are expecting for your antenna.
Okay, ma'am. Then the next question is how to extract RLC values from a 3D design in HFSS.
How to extract what?
RLC values.
RNC?
Yeah, ma'am.
I don't know if I understand correctly, but which values that you said?
RLC values, ma'am.
I don't know, but probably there is also there. I believe I never extract those values, but there is a lot of parameters that you can measure in your antenna design, and probably there is there in the far field of model termination plots that you can you can measure that, but I really don't know this one.
Okay,
I'm
ma'am.
sorry.
It's okay. Ma'am, the next question is can you suggest some free publications in antenna design?
Free applications.
Free publications, ma'am. Any journals?
Um, some free ones that you say the softwares.
Yeah, ma'am. Software versions also, ma'am. Free software versions.
Uh, I don't. I'm not familiar with free ones, but I believe there is a way to simulate antennas. I forgot the name of the software, but you have the results. But it's an open source software, but you have to put all the equations there. So it's a more programming software, but you have the results. Also, it's not that user friendly as in HFSS, for example. And also, I believe that the MATLAB has an antenna toolkit, and the MATLAB has the student version. So you can use it too, but I don't know if the MATLAB can. You can project your own antenna. You can design your own antenna. Maybe you have to use the models that are already there. So you put the frequency and the substrate height, but you can design from the bottom, as you can see in the HFSS. So I believe those two, but actually the first one I forgot the name, but I know that exists. And yeah, I believe that's it. I don't know a lot of free softwares to do that, because it's a very hard, I believe, task to do, to develop a software such as HFSS, and I don't know any free ones that are similar.
Okay, ma'am. The next question is what is S parameter?
S parameters?
Yes, ma'am.
The S parameters are the scattering parameters, which are the, as I said, for example, the S11 it is the power that you send in the port 1 and you receive in the port 1. So you have the reflection coefficient. In your antenna, for example, let me come back here where we have the S parameter. For example, here, we have the S11, which is the coefficient reflection. So I put the power in the port 1, and I read the power that I receive from port 1. So for my antenna, if the antenna is propagating the power that I'm putting in his input in the feed, so the reflection coefficient should be 0. But so all the power that I am giving to the antenna is propagating to the space. And to be 0 in dB, when you calculate it in dB, it should be minus infinite. So when you are looking the S11, for example, graphic, you expect that in the frequency that you want your antenna to work, the S11 level is the most negative possible. For example, and actually we have a standard common value that it's used that under minus 10 dB, it's a good impedance match that we call. So for example, here this antenna, a good impedance matching is between 100, about 27 gigahertz to 29 and a half 0.5 gigahertz. So between those two frequency, the antenna is working good. Minus 10 dB, it means that 10% of the antenna, if you calculate it in the dB expression, you're gonna see that 10% of the antenna power is reflecting in the input, but the other 90% is be send is propagated in the space. So in the S21, for example, I didn't put here a graphic to see a image, picture, but the S21, for example, is the transmission coefficient from the port 1 to port 2. When we measure, for example, in this setup, when we have two antennas and we put each antenna in one of the VNA ports, and we measure, we send a signal here. So port 1, and we measure the signal that we are receiving here, port 2. So we have the S21, which is the power from port 1 to port 2. So depending on this level, we can see if the antennas are working fine, if the antenna that is sending, it's okay, and the antenna that is receiving all the power in the sent by the first antenna. And if we have S31, for example, if you had another antenna here and connected to the VNA, also the port 3, the S31 would be the power sent by antenna 1 and received by antenna 3. And the S32 would be between antenna 2 and 3. So it's a parameter to measure the transmission and reflection of the antenna performance.
Thank you, ma'am. Thank you for clearing our doubts. And now it's time to express our gratitude. I am A. Kirtana from the Department of Electronics and Communication, St. Joseph Institute of Technology, St. Joseph Group of Institution, and the entire fraternity of the institution. I extend a hearty thanks to Ms. Camila Caroline Rodriguez for sharing your knowledge on basics of antennas. My heartfelt thanks to our beloved chairman, Dr. Babu Manogaran sir, for consistent support in conducting this webinar. My sincere thanks to our Managing Director, ma'am, Mrs. B. Jessipriya, and our Director, sir, Mr. B. Sasishekhar, for their constant support, and our Principal, Dr. P. Ravichandran, sir, for giving this great opportunity to conduct this webinar. And a special thanks to our department heads, Dr. C. Nyanakausalya, ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini, ma'am, Professor and Head, Lab Affairs, for their constant support. Last but never the least, I thank all our participants for their active participation. This webinar will be continued tomorrow by another eminent speaker, Dr. Carolette Blair, on insights to mutual coupling effects of patch antenna array using a full wave electromagnetic simulation tool. Interested participants can register through the same link. Thank you once again.
Thank you for the invitation. It was a pleasure to be here today with you. And I hope I could help and share a little bit what I use, what I know. And maybe we can meet in person in future APS events or collaborate with other virtual ones.
Sure, ma'am. Sure, ma'am. Yeah, you are always welcome to our campus.